Okay, so today we have Dr. Romit from Argonne National Lab. So Dr. Romit Maulik is an assistant computational scientist in Argonne National Lab. He is also a research assistant professor in the Department of Applied Mathematics at the Illinois Institute of Technology at Chicago. So he received his PhD in mechanical and aerospace engineering at Oklahoma State University. And his research interests are at the intersection of statistics and machine learning, dynamical systems, and high-performance computing with applications to many interesting problems in weather and climate modeling and nuclear fusion. So today, Romit is going to tell us a story about the reduced order modeling of high-dimensional system using scientific computing, using scientific machine learning. And Romit, the floor is yours.
Okay, great. So firstly, Angji, thank you so much for inviting me, and thank you to the members of the audience for taking time out of your busy schedules to be here. So like I was mentioning, feel free to interrupt me at any moment during the talk. I'd like to give informal seminars, and I think that's it relaxes me, and it probably relaxes members of the audience as well. So yeah, extremely happy to be here, and so let's get started. Okay, so this is the overall outline of my talk. So I'll initially give you a little bit of a motivation as to why I do the things I do. And then roughly the talk will be broken up into two chunks where I look at firstly deterministic dynamical systems and then stochastic dynamical systems. I'll scatter some examples throughout these in a slightly free-form manner. So I'm not going to be doing method introduction and an application. I like to keep it interesting. And then finally, I'll end with maybe a slide or two on some perspectives about where to go from here. And hopefully that's where we can all have a nice discussion. Okay, so in terms of the motivation, I mean, I'm probably preaching to the choir over here, but I do get asked this question by people who are unfamiliar with my work. Why do we need emulators or surrogates or reduced order models? There are various terms for this particular type of research. And the idea is that if you're trying to solve, if you're involved in a computational project where you have a campaign of simulations to run, for example, if you're doing geophysical forecasting where you need the forecast of a dynamical system each day, or if you're doing any sort of optimization or control of some costly engineering process, then it's obvious. Then it's obvious that there will be great benefits if you have tractable alternatives to these costly forward models, which are usually equation based, because you end up saving a lot in the long term. This also can be clubbed under the paradigm of sustainable computing. Just to give you a little bit of an example, the new machine that we're building here at Argonne, Aurora, it's going to be an exascale machine, is going to cost as much power to operate as the rest of the lab put together. And our lab is quite large. So you're looking at a lot of benefits if you avoid getting on Aurora for everything but the most crucial problems. So that's something that definitely motivates this body of research. More importantly, since a lot of the examples I'll be talking about today are purely data-driven, so there are approaches for actually beating the performance of classical equation-based methods or classical first principles-based methods, or at least augmenting them again within the context of your computational campaign. And then point 3 and point 2 are kind of related in the sense that frequently these data-driven methods can get you not only the increase in computational benefits, but also can give you more accuracy and stability, as we will see today. Okay, so with that, that's the motivation. So let me start with the first chunk of my talk today, and this is work that we've been doing for a while now, towards the tail end of my PhD and then beyond. With a large number of colleagues and contributors who are just summarized over here. So I don't have enough time to extol on the virtues of this large team, but you'll probably see this in the recording if you need further information. Okay. So in this particular talk, or in this particular section of the talk, I'm going to give you firstly a brief sort of review of some methods that I use on a very frequent basis before we go into the specific novelties. So a common strategy to build surrogate models is to leverage some sort of dimensionality reduction of your original system. This helps to obviously reduce the degrees of freedom of your system and then make functional approximation more tractable. So again, this must be very familiar to many members in the audience, but the idea over here is that if you have data from, is my cursor visible? I'm assuming it's visible. Okay, so if you have data from any simulations or experiments for various various control parameter perturbations. So this could be, for example, the physical parameter in your simulation, or different instances in time for which you're recording your system state. You could find both linear as well as non-linear methods to compress the dimensionality of your, or to compress the representation of your system. So in equation 1 over here, I'm showing a simple sort of projection-based dimension reduction, where if you identify a suitable coordinate transformation given by the columns of this matrix U tilde, you can reduce the dimensionality of your system just by performing this sort of inner product or this projection. U tilde for methods which are SVD based or POD or empirical orthogonal function, depending on your community, you may call it different things. Come from truncating the left singular vectors of this matrix of snapshots that you collected that I just mentioned previously. And this gives you the benefit of really ascribing the state that you obtain in the reduced order space to certain coordinate structures in your dynamics, which is very nice. Okay. But in some cases, these linear methods, which are generally projection based, are insufficient, insufficiently accurate for, or insufficiently efficient for in the sense of compression, for which you may need nonlinear compression methods. And there are several out there, which, for example, are nonlinear equivalents of the principal components like kernel PCA and diffusion maps, for example. More recently, with the large amount data in the talk today. So let's say you've been able to compress your dynamics, or compress not your dynamics, your representation efficiently into this low dimensional form. The idea that reduced order modelers try to leverage is that in this reduced space, you can still represent the higher order dynamics by learning a sufficiently complex function approximation. So in equation 3, what you see over here is that if I have a reduced order representation of my original snapshot matrix at different times, let's say this is a dynamical system, then the idea is to forecast into the future by learning a function approximation that looks at a window of information in the past. There may be connections here for someone who has been working along the lines of the Maury-Zwanzig type research, that closure can be accounted for through this sort of embedding of a memory term into your reduced order model. And so there are connections to some ideas which have been explored for a while in the dynamical systems community over here. Now, what a lot of research is doing at the moment is actually trying to find out novel ways to find what F is, in addition to the dimension reduction, which we'll go into. But if you can come up with, for example, data-driven methods to find what F is, then this reduces the burden of the first principle-based modeler, or at least reduces it enough to increase the accuracy, going forward. Okay. So let's look at a benchmark. So all that I've explained to you thus far is not new at all. So people have been doing linear dimensionality reduction since the late 80s, specifically for a lot of fluid flow applications. The idea over here, which I've demonstrated for the Burger's equation, is to then leverage this reduced order coordinate system with knowledge of your original dynamics. So if you have generated data from the Burger's equation, and you obviously know how the Burger's equation looks like, then you could use the projection of this system of PDs onto the reduced basis, which we call the Galerkin projection, to obtain a system which is the dimensionality of your reduced order representation, in this case small n. And so as you'll see shortly, this obviously has a lot of benefits in the sense of interpretability, in the sense of obviously computational efficiency as well, because your system is no longer a PDE. But you do run into some problems which are familiar, which may be familiar to people who try to numerically model PDEs on insufficiently resolved grids. So let's dive into that. Okay. Before I dive into that, let me also introduce another couple of methods that that we will be studying as an alternative to the Galerkin projection that I just mentioned. So I know Hangji has been working on this for some of her research, but for the benefit of the audience, I just wanted to very briefly introduce what the neural ordinary differential equation is. So the neural ordinary differential equation is this, these are equations that I've picked up from a paper that was published in 2018, but the broader idea of this has been around since the early 90s. I know Dr. Yanis Kevrakidis published a paper related to neural ODs in 1992 or 93. But the idea over here is to assume that the reduced representations of your dynamics can be evolved by some dynamical system, and the purpose of this particular algorithm is to learn this dynamical system. Is in particular, the right-hand side of this dynamical system is modeled as a neural network. So, for example, over here we have training data for A at different time steps, and our goal is to calibrate the tunable parameters of this neural network F for these, so that the predictions from this neural OD match in whatever sense of agreement you have picked a priori the training data that you've generated. And the interesting thing over here is that if you are a person who has done OD research in the past, then you are very comfortable in this particular sort of setup, because all you need to do is look at the concept of adjoint based methods or discrete time integrators. And then you can very easily construct equation 6 and 7, where equation 6 is basically a penalty for divergence from the true trajectory that you have collected training data for, and 7 is the adjoint problem, which calculates gradients of this divergence with respect to the trainable parameters, and then you put it into a stochastic gradient descent, and you basically optimize to get what the right-hand side of 5 is. Okay. So if you have collected state information for various dynamical systems, and nowadays with all the great measurements that are available for various types of natural phenomena, you can collect this information. You could learn dynamics without actually having access to the underlying principles, underlying first principle models, which is something that people are calling non-intrusive reduced order modeling at the moment. Okay. An alternative to the neural OD, which is something I actually started off with, so it's kind of backwards in the sense of my research agenda, but forwards in the sense of the logic, is to basically do a discretization of this equation on 5, and then in the backward Euler sense, and then add a few bells and whistles to the right hand side, when you're doing the discretization, and then come up with something called an LSTM neural network. The LSTM neural network, there's a lot of things happening over here, but what you really need to sort of take away from this is that for making any prediction at a time t, if the input is x and the output is h, then there is a dependence on the output at the previous time steps, which is something that is transmitted to something called the self state. The idea is that through the introduction of this sort of this horizontal line that you see over here, that's taking information from previous time steps, your algorithm is able to learn non-local dependencies in time from the data itself. So it's got a nice ring to it if you are looking at allowing for closure through for coarse-grained systems through the introduction of memory, and then so it's kind of like a dynamic implicit type of closure type framework that you can leverage. Okay, all right. So with these three sort of benchmark methods, let's move into our first example. Okay, I'm going to start small before I gradually ramp up the complexity of my examples. So the first example that we look at is the viscous Burgers equation, like that I just introduced. So over here, I have a system that has a sufficiently low viscosity to generate some hyperbolic behavior. So for example, over here, the viscosity is 2.5 e to the -3. So it's very, convection, the convective term dominates the diffusive term. In order to solve this system for a representative initial condition, you need a discretization on the of this one-dimensional space into 2048 degrees of freedom, and I'm using the finite volume method with a suitably chosen, I think this was like a Rusinov type Riemann solver to solve this, the idea over here is that can we reduce the dimensionality of the system sufficiently so that we can get a obviously compressive benefit, but also can we preserve the accuracy of the system. Now, the one thing I'd like to mention over here is that, firstly, this training or whatever, this ML concept over here is applied to many different initial conditions, which are sampled by superposing frequencies in the physical domain. But the dynamics of this particular system are generate standing shocks. So you can see over here, the blue lines are the initial condition, the yellow lines are the final condition. And so there isn't a lot of advection dominated behavior yet. And that's because we want to understand the nature of the closure that we want to do using machine learning rather than just the ability to capture propagating discontinuities. I have an example for that shortly. Okay, so let's do the Galerkin projection discretization and deployment in a reduced basis which has only 3 degrees of freedom. So the green lines that you see over here are basically the trajectory of the system on just 3 basis vectors, using 3 basis vectors which we obtained using the POD or the SPD or whatever you like to call it. The truth and the ML predictions are on the actually all on top of each other on the yellow line, or the line that looks like it's yellow over here. So at the moment, our hypothesis is that because the Galerkin projection is in some sense a projection of our equation onto the reduced space that doesn't have sufficient support to resolve all the dynamics, that you get this this divergence. Okay. So in the next slide, we are going to do a little bit of analysis to confirm this hypothesis. So on the top left, you have a angle average energy spectra for the solution at the final time step between the 3 different reduced order modeling methods and basically the higher order finite volume method that we used on the 2000 degree of freedom Cartesian grid. And if you were to compare the spectra, which is supposed to follow the k to the -2 scaling in the dotted line over here for the Burgess turbulence, you can see that the Galerkin projection has a higher residual compared to the ML alternatives, which in some sense is one sort of confirmation of the hypothesis that the Galerkin projection was struggling to perform a closure, whereas the LSTM or the neural OD was able to implicitly learn this closure, right? So it's sort of a non-intrusive learning of dynamics, and the dynamics, since it's coming from examples of training data, also has to learn a closure at the same time.
Romit, can I ask a question?
Oh yeah, absolutely. Go ahead.
So for the neural OD, you described it in the setting of an OD. Now you're trying to learn a PD. The A in your neural OD, what would it be? Would it be just Galerkin modes, or?
It would be coefficients of Galerkin modes, coefficients of the POD modes.
Just 3 of them, right?
Just 3 of them, yes. So we're learning a three-dimensional system as a proxy for a 2000 dimensional PD. So
I see. Okay, thank you.
Sure. Okay, so all right, so the spectrum reveals some interesting information for us. Let's look at the physical space, and if you were to zoom in near these discontinuities, you would see something that's common to, or common in the sense it strikes fear into the heart of people who do numerical discretizations. You see the presence of these Gibbs types oscillations, which are sort of emerging from these regions due to the Galerkin projection, which the neural OD and the LSTM are able to suppress satisfactorily. Okay, so this is kind of 2 points of confirmation of the fact that our ML method is in some sense implicitly learning to correct for these deficiencies of the standard projection-based reduced order modeling technique. I mean, the neural OD and the LSTM in this case are also being deployed in a projection-based method, but generally when people say projection-based ROMs, they talk about the Galerkin or the Petrov-Galerkin type projection methods. Okay. So that was the first example. Okay, so let's look at another example over here where we have to, in some sense, broaden our technology net to solve a slightly more complicated problem. So I'm going to 2 dimensions over here. And instead of the Burger's equation, I'm going to the implicit sort of shallow water equations. So these equations are, are 3 coupled PDEs, which have 3 conserved variables, rho eta Vx, and rho eta Vy. If you set rho equal to 1, then eta stands for the height of a wave, and Vx and Vy correspond to x and y velocities, and this is a prototypical system for a lot of geophysical dynamics. So this is nice. It's getting a little more realistic. The system is parameterized by initial conditions like the last case, but here we basically have a quiescent condition for the velocities, but a Gaussian sort of perturbation for the height, which is controlled by a control parameter which indicates the center of this Gaussian. So X bar and Y bar over here are basically varied, and the idea is, can we build a reduced order model, a surrogate model that given an X bar and a Y bar that was not previously used for any training data generation, produce the trajectory accurately. So that's kind of the reduced order modeling idea. The boundary conditions over here are periodic, and the grid is a 64 by 64 discretization, and there are 3 conserved variables, so it's 64 by 64 by 3 essentially. And the reduced order modeling or the requirement or the compressive efficiencies that we bring it down to 6 degrees of freedom, as you'll see shortly. Okay, so over here, when you take a problem like this, which is basically advection dominated, you have these moving sort of discontinuities. Let me see if I can pull up a lot of this. So this is in some sense how the solution evolves. This is the first degree of freedom, and you see it's definitely more advection dominated than standing shocks. So you see that the POD type, the linear dimensionality reduction methods are going to suffer quite tremendously in representing these types of dynamics. There are methods out there which can improve on linear dimensionality techniques if you know a priori the transport speed. So that lets you build slightly better reduced order models, but our assumption here is that we don't know the transport speed ahead of time, and so it's a difficult task in that sense. So over here we had to rely on something a little more state of the art when it comes to compression, which is a deep learning autoencoder or convolutional autoencoder. The idea of this setup is to have a neural network that essentially learns the identity function, but learns it through an architecture which has this hourglass type shape. At the middle of the hourglass is a representation that is, depending on how you devise it, sufficiently compressed compared to the original dynamics. But if the identity function is learned completely, is learned competently, then you can take the intermediate representation and pass it through the bottom of the hourglass, the decoder, to reconstruct the high order or the full order snapshot accurately. So over here, since we have the luxury of having a structured grid, we don't always, and so there is an example where we don't have that luxury. We can basically strike these sort of filter kernels over the image and learn this compressed representation. Okay. So how does this over here, we only looked at the LSTM, but how does this reduced representation coupled with an LSTM do for a test example? So as you can see over here, for these 6 dimensions that we've compressed our original system to, for a test condition, our dynamics can be predicted sufficiently accurately. However, there's a limitation over here, and this is somewhat of an open problem for people who are doing machine learning applications for science, in that how do you interpret these curves that I'm showing you over here, right? So the curves that we're showing you over here in this example are like, Mohammed said, they are the coefficients of these POD modes. And so there is a meaning to what each of them are representing. Over here, you're getting something similar and you're able to forecast it well as well, but all bets are off as to what this actually means. And so there are methods out there which try to enforce orthogonality between these things, or orthogonality in the sense of not being correlated, not literally in the mathematical sense. But it's still an open problem as to what they mean and what, how we can actually ascribe physics to what you're seeing over here. But at least in the sense of, in the engineering sense, the forecast is being made by a reduced order modeling technique.
So, Romit, can I
yes.
ask a real quick question here? On
Sure.
the previous slide, you mentioned the term forecast. Are you actually doing future predictions, extrapolatory predictions with this? Because that's always a kind of a delicate thing.
Yes, yes. So when I mean forecasting, I mean for a new value of X bar and Y bar. So it's definitely parametric reduced order modeling. Yeah, that's a very good question, right? So
okay, so you're not going out of data with it, then, I don't think. Oh,
no.
Okay, perfect. Thank you.
Yeah.
Thank you.
Yeah. Mm-hmm. Yeah, so it's a good question because people misuse this jargon a lot. I mean, some people think forecasting means it's like going into the future. That's what the geophysical community calls it, whereas I'm calling it in this particular context prediction for a new initial condition. Good question. Okay, so if you were to look qualitatively at the ability of this reduced order model to reconstruct our state, the high order state for on the Cartesian grid, you can see that for the compressive efficiency that we had demanded, which is 6 degrees of freedom, you're able to recover the original evolution of the dynamics sufficiently accurately. Whereas the Galerkin projection, it requires an order of 100 modes to converge the the original fidelity, and that is something that that sort of speaks to the power of these nonlinear dimensionality reduction techniques in terms of how they can solve the limitations of the classical linear methods. So how do we use this? I mean, so if you're looking at projects where you're okay with some sort of broadband error. So when I say broadband error, I mean you're looking for quantities of interest rather than convergence, for example. These are some things that we cannot guarantee here. Where the POD Galerkin projection will converge as you increase the number of degrees of freedom, but with the autoencoder, that is not guaranteed. And in the sense of an aggregate, yes, as you increase the latent space of this autoencoder, you get better and better ability to represent the original dynamics, but it's not guaranteed. Over here, you can sort of compress your system, put it into some outer loop consumer of the reduced order model, and get quite significant benefits. So let me give you an example of that. I'm sorry to the mathematicians in the audience, but I like to put in a couple of sort of engineering examples just to make myself feel good more than anything else, I guess. So this is a collaboration I had with the. Was there a question? I'm sorry. So
yeah. Sorry. Can you go back to your previous slide with the So I know you were talking about interpretability for these sort of the latent dimensions from the convolutional autoencoder are kind of hard to interpret. Now, can you go back to the next slide, this one? I know there's been some work on relating convolutional layers to differential operators, and I know you can sort of see this Q2 and the Q3 look a lot like X and Y derivatives of this sort of function. Is that something that you've looked into for this? Because it looks like your autoencoder is learning some sort of derivative information along these coordinate axes.
So I know I've read a couple of papers from a collaborator of mine, Arvind Mohan, who's explicitly built the first layer of a convolutional framework. I don't know if he was doing it for an autoencoder, but he explicitly embedded derivative information into the first layer of a convolutional neural network. So the idea is that these filters can behave like finite difference operators. So you make them non-trainable, and so what happens in the first layer as you pass your data in is that not only do you give the raw data into the deeper layers of the network, but you also give derivative information deeper in there. But the thing is, if you were to restrict yourself to derivatives, you would have to keep the dimensionality the same. I mean, I understand what you're getting at.
I see. Yeah.
But we're trying to narrow the dimensionality, right? So it's kind of so in that sense, my guess is, it's possible that the input layer to the autoencoder has some correlation with the derivatives. But we are looking at what the reduced order representation is and how it relates to the high order dynamics or the full order dynamics.
I see. Thank you.
Sure. Okay, so back to my example. So over here, we basically collaborated with the Energy and Global Security Division here at Argonne to deploy these methods for something that was a little more practical. So over here, we are trying to run simulations of an internal combustion engine, multi-phase simulations of an internal combustion engine, which if you ever try to do that, you'd realize that a lot of the computational bottleneck happens because the geometry near the injector. So you have fuel that is injected into a larger chamber, and the geometry near the injector is extremely complicated, and that's where the time step of your numerical integrator for your PD becomes extremely small. So in some sense, the idea is if you can bypass the simulation of that region and just model it as a boundary condition to your bigger chamber, you can end up getting some tremendous benefits. So over here, what we did was we generated some full order simulations, because you can't get away from that on a large machine that we have here. Each simulation, each point that you see over here, took a week to run. So it was extremely complex, extremely complicated. And but all that each of these simulations boiled down to be was a bunch of snapshots at different times and for different parameters. These are two parameters: the amount of nitrogen in the fuel and the ratio of air to fuel, or fuel to air, one of the two. And so at different times and for different parameters, you get these snapshots for the injector entry region into the main chamber, which we then use the same method, the same idea that I explained to you for the convolutional autoencoder, except we used a regular autoencoder because this was an unstructured grid with a latent dimension space, which in this was 25. So we needed more expression, but it was completely worth it, as you'll see. Instead of using an LSTM or instead of using a neural OD, we started simpler, and since simple worked for us, we stuck to that. In this case, it was a Gaussian process type regression that was calibrated and that was parameterized by the value of these two parameters and time to essentially predict the boundary condition for the chamber, right? So instead of simulating the injector, we just simulate a boundary condition as a patch on the chamber. And we actually went ahead and deployed it. And as you see, after deploying this and just using the regular set of multi-phase PDs for the main chamber, you're able to, in the top row is the truth that took an entire week to run, and the bottom row is something that took 6 orders of magnitude less time to run, because we did not simulate this region over here, but just simulated the prediction from the autoencoder as a circle, essentially. And you can see on the top left, I'm showing you the droplet radius of the fuel that after 280 microseconds of injection, and this is the flame front on the right, and both are predicted quite nicely for using the reduced order sort of boundary condition. So in some sense, I've walked you through the inception of the method all the way to the deployment. So obviously people are quite happy about it here. And of course,
Romit, can you comment on if you can get some kind of accuracy guarantee on these kinds of prediction, or what the general observation would look like for this?
Yeah, I know this is a mathematics seminar. No, I cannot give you anything at the moment, unfortunately, because this is very much a sort of engineering-ish deployment of these reduced order modeling methods. But the one thing that we did build into this framework was, because we had a quantified sort of uncertainty type prediction, at the very least, we could, with some confidence, say we should not probably use this forecast, or we should not probably at this moment use this this prediction. So that is something that obviously can be done with these ML type methods, but guarantees is a strong word for that, I think. So
yeah, I see. Thank you.
Mm-hmm. Okay, so I'm already late, but let me continue. So I don't know if I'll be able to get to the stochastic portion of my talk today, but let's finish up the deterministic portion. So I've talked about advection-dominated dynamics. I've talked about closing reduced order models. So I wanted to complete the discussion for deterministic systems by spending a little bit of time on chaotic dynamics. So for systems, for example, the ones that I've mentioned over here, the Kuramoto-Shevasinski equation, depending on the choice of the domain size in this particular case, or the equivalent transformation of this is the choice of the viscosity, you may get different behavior of this system in the long term after long term simulation. So for this particular system, 16 and 17, as you evolve this state, you will end up getting what we call a chaotic attractor. And so the idea over here is to use the system to develop new methods which can not only make short-term predictions of our dynamics, which is obviously desirable, but also respect these sort of long-term steady state type properties, which actually a lot of classical time series modeling methods, such as the LSTMs and the neural ODs, suffer from, as you'll see shortly. Okay. So the idea over here is was essentially, again, a result of us trying to use a neural OD to forecast the Kuramoto-Shevasinski equation for a novel inertial condition, and we realized that we were running into some troubles. And so in order to address that, what we did was with my summer student, Alec, who is graduating at the University of Wisconsin. He's finishing his PhD at the University of Wisconsin this year. And of course, other collaborators at Los Alamos and Argonne. We developed a novel neural ordinary differential equation that in some sense sort of added an inductive bias, so to speak, into the ML frameworks. So what you see on the right hand side over here with the F tilde over here is the neural OD that I talked to you half an hour ago approximately. It's just the same, except that now I am not performing this forecasting, so to speak, on the reduced order representation. You can assume U to be the full order representation, which in this case is 64 degrees of freedom. The reduced order will come in, I promise you, in just a moment. What we did over here was after finding that the guy on the right hand side, gives us pretty awful predictions for the statistics of the chaotic attractor, we added a linear term to the right hand side of the neural OD, just like you might add a regularization to your neural network in some sense, except that this linear term over here was designed just like a finite difference stencil. So we know that a linear term exists, and that you can use like a discrete representation of this linear term to be dissipative essentially, right? And so if we have a convolutional kernel, this is a continuation of the discussion I was having with related to the previous question about kernels learning derivatives. So here we actually embedded information of a supposed derivative that can be learned through optimization into our neural network, except that we enforce symmetry to guarantee its linearity. Then we can have a neural network that hopefully is able to do better on this chaotic type of time series data. So let me show you some results first, and let's do a little bit more analysis about what's happening here. So on the top row, you see the true data. So I pick up a random initial condition, and I know that my Kuramoto-Shevasinski equation, if I put it through my numerical method, which in this case was a spectral method, then it should give us a certain evolution in the short term for 50 time minutes, and then obviously the chaos takes over, and then you diverge completely in the sense of the state. And then you get something in the long term as well. If you use a regular neural OD, the one that I just discussed a while ago, you will see that in the short term, again, until you cross that Lyapunov time sort of barrier, you stay stuck to the original trajectory, so it looks okay. But in the long run, you'll see that there are these high wave number behavior that emerge, and frequently your neural OD just blows up. It doesn't even run that long, and that's kind of the problem that we were trying to solve. So in the last two rows over here, we have this idea of the linear nonlinear decomposition on the right hand side, except that for the The third row, what we are doing is we are cheating. So we know the Kolmogorov-Sierczynski equation, and we know how the linear term should look like. So we directly sort of embed the linear term on the right-hand side rather than learn it through the approximation, to the optimization. And we see that it stays stable and bounded. We will do more analysis in a while, hold on. And in the bottom, we have what I just proposed, which is you have a linear term that is learned through the optimization, as well as the the nonlinear term on the right-hand side. And again, in both of these situations, we see that the method remains stable. If you are to look at the short-term tracking error, again, there's not much difference between the different methods, because again, the problem was not in forecasting in the short term; it was basically forecasting in the long term. But if you look at the statistics of our forecasts in the sense of the chaotic attractor, the statistics at the steady state, all you got to do is construct a probability density function between the second derivative of the state and the first derivative of the state as it bounces around in the long term. And you get, at least for the true data, you get this really cool this pear-shaped or peach, I don't know, some fruit-shaped attractor, which tells you that there is some structure underlying this chaotic observation in physical space. The nonlinear and linear decompositions of the system are able to represent or capture this behavior quite nicely, as you can see over here. But the regular neural OD, if at all it manages to make it thus far, it usually blows up before you see this kind of crazy behavior, which the statistics are not basically observed. And of course, we tested this on multiple different initializations. So you can see there's an ensemble average that we're doing over here. So what it's telling us is that linear nonlinear decomposition is able to deal with the problem of the chaotic attractor quite nicely over here. Okay. But there's more. Since we have this linear term on the right-hand side at the moment, this opens up a wealth of approaches that have been studied quite deeply for the last 30 years. Even if you talk only about the Kolmogorov-Sierczynski equations, for doing reduced order modeling now. So far I have built a surrogate of a PD. Right now I still haven't reduced the dimensionality of my system yet. So by leveraging the eigen decomposition of this linear term, as you see over here in 22, I can find a projection operator using inertial manifold theory to split my system into a set of resolved coordinates, as you can see in equation 18, and a set of unresolved coordinates or ignored coordinates in equation 19, and then couple the two using the assumption of stationarity for equation 19. So if you set dq by dt equal to 0, you get this expression over here, and then which you can solve, and then you can set q to be equal to 0 as the first step of a nonlinear solvent, and essentially couple equations 18 through 20. The P over here is the projection matrix that I told you that basically uses the eigen decomposition of this learned linear term. So it's not even that the linear term needs to be known ahead of time. But by setting up this particular problem, you can actually get a significant reduction of your surrogate model, which in terms of its dimension, down to the underlying dimension of the attractor, which in this case is 16. So over here, I have three curves that are basically, in some sense doing the same. So let me explain what these curves are to you. So the orange squares over here are us actually solving equation 18 and just setting q equal to 0 over here. So it's the Galerkin approximation. So it's truncation without closure. Closure is happening through equation 20. We don't do that, right? And you can see the errors are higher. So the KL divergence over here corresponds to the difference in statistics at the steady state between. So I'm talking about the KL divergence of these two statistics, for example. So the blue circles over here are the approximation manifold that I was talking about. So that's basically evolving equation 18 with the q on the right hand side being replaced by equation 20. Okay, and you can see that's more accurate than Galerkin because we do perform the closure in the system. And for the Kolmogorov-Sierczynski equation in particular, we have the benefit of doing something called postprocessing, which was done way back, in the early 90s again by Dristiti and by Yanis Kefakidis, where you could evolve the system according to 18 and set Q equal to 0, and then perform this correction using equation 20 after the fact. So you have evolved your entire system in P, stored the snapshots of P, but then you reintroduce Q into it using equation 20. And you can see it's obviously somewhere in between the approximate inertial manifold, which happens at each time step, and the Galerkin, which happens, and the Galerkin. And you can see as you go down to 16 degrees of freedom, you basically then start matching the statistics of the full system, which basically alludes to the intrinsic dimensionality of the stochastic, the chaotic dynamic system. Okay, so this is nice. So in some sense, we've kind of, just by introducing a simple linear term on the right-hand side, we've kind of unified 30 years of research into inertial manifold theory with the neural OD. So we're kind of proud of that, and we will be putting out a preprint on this shortly. Okay, so where are we at with this current line of thought of research? So what we are doing now with colleagues at Argonne and Los Alamos are also studying. I didn't talk about Hamiltonian dynamics because, in some sense, my collaborator Chi Tang at Los Alamos is the PI, so to speak, of that. So I think he should speak about that. But what we have done is we have also developed surrogate models for dynamical systems which have which have a Hamiltonian, so they are conservative. So we have conservative, we have chaotic, we have advective, and so on and so forth. So we're kind of trying to set up this multi-pronged type of research direction. Another thing that interests me specifically is because of the really strong emphasis on a lot of geophysical applications here at Argonne. I know I showed you a combustion application today, but there's a strong emphasis on geophysical stuff. There is a need to rapidly adapt to new data that's coming in. So Argonne has a weather station over here, and we have a portal to which we can hook up to using a Python API that continuously streams the latest data. So people say, okay, your surrogates are great, we are fine, but is there a way to retool them as soon as we get new data? And so data assimilation is also something that we are that I have been doing some work in and integrating these methods to them. And finally, the problems I've shown you today are still relatively small, but we are looking at really scaling these up in terms of the sizes of the applications, the number of surrogate evaluations that are happening in concurrency, and so on and so forth. So there is a scaling question that also needs to be solved over here. And of course, there are many application areas, like I just mentioned. Okay, so okay, I have 13 minutes. Should I take this risk? Let me do it and see how long it goes. Okay, so the second part of my talk today was supposed to be, or is, related to building surrogate models like I just did, but over here we are talking of stochastic dynamical systems, not deterministic dynamical systems, and this is collaborative work as well, as everything is nowadays. So let me briefly just run through the background of these this stochastic branch of my research. So over here, what we are trying to do is essentially build surrogates for dynamical systems which may have a form as shown in equation 23. So over here we have you have an Ito stochastic differential equation which is driven by a drift and a diffusion over here, where the forcing that happens to this dynamical system is given by a Wiener or Brownian process. So this is the most common form of a stochastic dynamical system, and as it has been studied quite nicely, and there are a lot of nice theoretical properties for this. For example, if x over here refers to a particle, right, that is evolving in time, then if you initialize x again and solve the system again, you will probably get a completely different trajectory. And so if you do this again and again, just like you're doing Monte Carlo, you basically end up with you could histogram, for example, at different time steps, the behavior of these particles, and construct approximations of densities over time. The issue is that over here, X can get really, really high dimensional. And so these histogram or Monte Carlo techniques suffer then from the curse of dimensionality, as I'm sure you're aware of. So it's very useful for people to work in the density representation of these dynamical systems, which, for example, is given by the Fokker-Planck PD or the backward Kolmogorov PD, if you are coming from the statistics background, which is given as such over here on the right-hand side. And there's been a lot of work in actually using, for example, physics-informed neural networks, from the group in Brown, and actually learning equation 24 given examples of training data, or even without examples of training data, using these constrained optimization methods. Now, what we are interested in is something a little more complex, which is systems where the right-hand side of the SDE, the particle representation, also may have some non-Brownian or anomalous diffusion, as we call it over here. The L stands for potentially something like a Levy process, a jump process, which then in many cases does not have a closed form Fokker-Planck or backward Kolmogorov equation. But for example, if you assume that there's an additive noise with a Levy process, in which case there is a Fokker-Planck representation, you see that the right-hand side of the PD compared to the previous one gets extremely ugly. You have this non-local type of term, which in higher dimensions becomes quite intractable to solve efficiently. So our goal is, and even if you're looking at something like physics-informed neural networks, you probably have to use automatic differentiation to train these networks, which is possible for something like this because you essentially have integral order derivatives. But over here, since this is a non-local term, you end up having to do some discretization. And so the benefits of working in the PD representation with pins are lost. So how do we bypass this particular approach? I have a little literature review here, but since I have only 8 minutes left, let me quickly go on to the bulk of my idea. So over here, the idea is that can we use methods from generative machine learning, which is a whole body of work that's happening in computer science, and actually even before that in applied mathematics, to learn density representations of particle observations, right? So the way a normalizing flow works is that it assumes that there's an invertible transformation between a simple density, which for all purposes could be an isotropic multivariate Gaussian, to your target density, which is unknown. Okay, so it just assumes that there is a transformation between them, and that if this transformation happens between the support of these two densities, you can, and is invertible, you can basically have a unique relationship between every sample from the Gaussian to every sample that you observe from this unknown density. Okay, and so the idea is that if you use a neural network to represent what this transformation is, which can be composed with each other because the composition of invertible transformations is invertible, you could set up a pipeline to learn the density that you have from just the particles. Okay, and so the way that is constructed is sort of highlighted over here. You assume that the relationship 30 holds for your particular system, where the left-hand side is this unknown density that you're trying to learn. The right-hand side has a known density P of Z, which is Gaussian in this case, and you know that there is a invertible transformation T that takes from the particle you observe to a particle from the Gaussian. And then this equation basically summarizes the law of conservation of probability. And then if you take the log of both sides and try to minimize the difference between these two guys, you get a cost function that you can put into a stochastic gradient descent optimizer for different observations of X. Okay, so that's kind of the background. What we did in this particular study is that we constructed this relationship using an affine coupling called the real MVP. But more interestingly, we made this transformation a function of time, because we're looking at a stochastic dynamical system. So we know that not only is the target density related to the Gaussian invertibly, this invertible relationship is also a function of time. And so what we want to do is learn the evolution of this density over time, even though the latent density remains a Gaussian forever. So after setting up 32 and 33, as I see over here, and performing this particular this sort of optimization for a problem which in this case is two-dimensional. It's not super high dimensional yet, but that's going to be an extension. But you see on the right hand side, it's driven by a purely Levy noise, which is additive in nature. You will see that the normalizing flow, which is being sampled from in the bottom, is able to predict this really interesting evolution of the density. So initially the density is just a bivariate Gaussian. So in some sense, the transformation between the target and the latent is identity. But the evolution of this density over time using this Levy type of right-hand side, it leads to the formation of this multimodal type of density, which is really cool. And the normalizing flow is also able to, pick up this type of behavior over time. So, and of course, this is not the only assessment we did. You can see more at this link over here because I'm running out of time. But what this is very useful for is learning joint densities between poorly observed quantities in the geosciences. For example, one piece of work I'm doing now is actually learning the evolution of the of the state given by paleoclimatic records. So if you dig the permafrost in Greenland and you measure the calcium isotope over there, then you're looking at a time series which looks very much like a stochastic dynamical system. You have periods of Brownian type motion, and then you have sudden jumps which represent some potentially catastrophic events in the Earth's climate, such as the ones that we are living through at the moment. So there is a value to learning the density of the system in as much as that you can sample the density and extract quantities of interest such as transition probabilities and so on and so forth, mean exit time and so on and so forth, which is something that we're really keen on studying further. Okay, so that's kind of what I was talking about here in terms of extension. So I think I'm right on time. So I will just stop here with one slide that summarizes which direction I'm trying to take this research interest, these research ideas that I've shown you. So there's this quote by Mark Twain that I find really that it resonates with me and my peers who are working in this area. It says that when you're on the side of the majority, it's a good time to pause and reflect. So if you're doing scientific machine learning research, especially within the DU at the moment, you'll see that the grants are coming easy, the papers are coming easy, the citations are coming easy, and it's a good time to not get sucked into doing reinventing the wheel, but really making sure that you address sort of these open questions out there, which I've kind of pulled from the basic research needs workshop report that the DOE published in 2019, which is that we need to make our ML methods more domain aware, more interpretable, more robust, in order for them to, and we need to hold them up to the standards that we hold our classical state-of-the-art numerical methods up to, in terms of, like Hangji asked, guarantees and property preservation and so on. So that's definitely a like a broad goal of a lot of the research that not just me but all my collaborators over here are also trying to pursue. Okay, so I will leave up this slide for some acknowledgements that supported this research, and thank you very much for coming, and thank you for your for your attention.
Thank you, Romit. This is great. Such an interesting talk. Do we have any questions from the audience?
Angie, can I ask a question? It's probably a very naive one. So you said that basically there is no way, or at least you didn't present anything similar to convergence, right? That there is no way to quantify the accuracy as it depends on dimension, in very general terms. So in this in this realm, if you will, is there any measure, any metric of how well you are doing in general? So beyond just looking at plots and saying that, okay, so there is something that resembles something else in the eyeball norm. Is there any way to go at least one step beyond that? maybe not necessarily proving theorems about convergence, but at least some, like, something that will allow a quantitative assessment of how, how adequate is the prediction, if we call it a prediction.
That's a very good question. So the classical way to do these things is to have some held out data ahead of time. So you're generating training data and you separate a part of that out to just be your a posteriori validation data. This is data that you never look at. This is not data that you report as your metric. This is data that you just use to choose your model. So since you're doing, for a lot of these problems, you're doing non-convex optimization, you will save a model after this training or whatever you call it, this optimization. You will not immediately make a publication quality plot because, like you said, it's difficult, to go down that route without any guarantees or without any theorems. But what you do is you look at this held out data set, and if you think that your model is not performing up to your requirements for computational accuracy or for whatever metric that you decided, you go back, you feedback, you generate more data, you retrain. Again, you keep a portion of data that's held out just for validation, verification. Once this inner loop is in some sense complete, you are able to perform well on this validation data, then you do these assessments on test data, which is another set of data that you hold out completely and never look at. And this is the data set which I'm showing you for all my assessments over here. So that this is the way you kind of, it's a hack at this moment, I'm sorry to say, but it shows you some quantitative, it lets you trust your behavior, at least in slightly more than just the eyeball norm, as you said. So.
Thank you.
Mm-hmm.
Thank you.
Okay, great. Do we have any other questions? I think we're running out of time. I did want to ask a bit about that linear term that you added to
Sure.
your model. I don't know if we have time. Maybe let me start recording. And thank you all for joining today's seminar. It's very nice talking to everyone.
Yeah, I can stick around for a half an hour more. So if